Alright guys, welcome to today's note section on our new unit of nuclear chemistry. As you can see behind me, we're going to be talking about some of these things that are up here that you're very familiar with when you hear the word nuclear chemistry. Case in point, we're going to be talking about these reactors that you see and what those typically mean, and we're going to be talking about the reactions that are involved with nuclear chemistry. So hang on a second. Before we get started, I actually don't want to do this inside of the classroom like I originally thought. Let's actually take this somewhere different. Alright guys, what's going on? So I told you we were going to get out of the classroom a little bit and take you somewhere kind of cool. You can kind of see behind me a little bit. We are near the entrance to the Savannah River site located in New Ellington, South Carolina. This is home to a nuclear facility that was built during the Cold War era when nuclear weapons were just starting and we were figuring out how to weaponize these nuclear reactions. Over time, the U.S. Department of Energy has restructured what the Savannah River site is being utilized for, and if you pay attention to the news, you do see it come up fairly often with housing waste material from not only our country but other countries as well. So within this note section, what we're going to talk about is the basic foundation to nuclear reactions, what radioactivity is, what the radioactive particles are, and the difference between fusion and fission reactions, which are really important for what goes on in the Savannah River site. So let's go ahead and get started with this basic foundation into nuclear chemistry. Alright guys, in this note section, we're going to start our introduction into radioactivity, how it was discovered, who are some major components of its discovery, and along with the different particles that are involved with radiation. So first off, we're going to talk about the discovery of radioactivity and primarily focus on two people. The first guy is a French scientist by the name of Henri Becquerel, and in 1896, what he ended up doing was putting a photographic plate in a dark desk drawer that also had some crystals of uranium, and this was completely done by accident. He didn't do this on purpose with the mission to figure out radioactivity. He just put in an old photographic plate in his desk drawer that just coincidentally had some crystals of uranium. And the next day when he came back into his office, what he ended up finding was that the plates were exposed, and I'll show you a picture of what he saw in just a moment. And then he concluded, after some kind of thinking of wondering what happened, was that it was the uranium must have released some sort of particles of energy that caused the photographic plates to become exposed. He ended up then terming this radiation, and he used a different term for it, but overall it was radiation that he first discovered. This is what the photographic plate looked like that was exposed in the desk drawer from the uranium crystals. And what we mean by a photographic plate is just old school photography used these big plates in order to expose the image on them. And this is what ended up happening to his photographic plate that then caused him to figure out that the uranium was releasing some form of energy. So that now leads us to talking about Marie and Pierre Curie, a husband and wife team. And what they ended up doing was discovering two radioactive elements, and they discovered both polonium, named after their homeland of Poland, and radium. In 1903, Marie was the first woman to ever receive a Nobel Prize for the work with radiation. And in fact, Marie was also the first person to ever win 2 Nobel Prizes for her work. So she was the very first woman to win a Nobel Prize and the first to win 2 Nobel Prizes, which is a huge accomplishment. in the field of science with winning Nobel Prizes. So to focus specifically on Marie for just a moment, she conducted research on how radiation could be used in order to treat cancer. So all of our cancer treatments can really go back all the way to Marie Curie with how we deal with radiation now to treat cancers. However wonderful that this may be, and it was, she devoted her entire life to science, to figuring out how to cure and treat cancers, and she didn't realize that high doses could also cause cancer, and she ended up dying of anemia. So she was looking into radiation to treat cancer, but in the process never realized that such high levels of radiation could actually cause cancer. In fact, her notebook is still radioactive more than 100 years later. If you go in with a Geiger counter that measures radiation and put it up to her office, her desk, the doorknob in her office, you still find high levels of radiation from the amount of work that she did with radioactive particles. So moving on now, let's actually talk about what radioactivity actually is. So radioactivity is when the nucleus of an atom becomes unstable and then it's going to decay, meaning it's going to break down. When an element decays, it's going to release particles of radiation, and we call it being radioactive, thanks in part to Henry Becquerel and Marie Curie's work that we defined what radioactivity is. There's always a small amount of radioactivity in our environment, and this is just simply called background radiation. So in terms of radioactivity being dangerous to our health, this occurs simply when a person is exposed to high levels of radiation. And once you get such high levels, then you could probably end up having cancer being formed from such high levels of radiation. But the background radiation that exists in our normal environment is simply nowhere near any sort of level to be of concern to you. So now let's talk about radioactive elements. Large atoms tend to be unstable and be classified as radioactive. This is due to the ratio of the protons and neutrons in the nucleus being so weird, and they are so skewed from the amount of protons to the neutrons that they're actually just going to decay in order to become stable. A great example of this would be uranium. Uranium is one of those radioactive elements. All elements after number 83 on the periodic table are considered radioactive. All elements after element number 92 are synthetic, meaning man-made, and we can create them in a particle physics lab. The synthetic elements are very unstable and only exist for a fraction of a second before they begin to decay. So this is why we use particle accelerators in order to smash atoms together to see the results of the atoms being forced together, and this is how we essentially discover new elements, or quote unquote make new elements, by smashing particles together. The amount of time that it takes for a sample of radioactive elements to decay by half is called the half-life. So as an example, it takes 5,730 years roughly for a sample of carbon-14 to decay by half. So if you start with 5 grams of carbon-14, it'll take 5,000 years to decay to half that amount. This is very beneficial to know because this is how we age fossils and rocks. This is how, when you read in the news that we can date fossils or rocks to a particular time frame, we use carbon-14 dating and looking at the half-lives of different radioactive elements to figure out how old these samples are. When you get into chemistry and specifically focused on the nuclear unit in that course, you'll look at the equations that are used to calculate half-life and do a little bit of math involved in figuring out half-lives of certain elements. Now let's talk about the radioactive particles that exist. The first are alpha particles, and an alpha particle is simply a helium nucleus without any electrons, and that's what makes it radioactive, is it's essentially helium without the 2 electrons. Next, we have beta particles, and this is where the electron is emitted from the atomic nucleus. And lastly, we have gamma particles, and these are your high energy electromagnetic radiation. The gamma particles are essentially the big boys of the radioactive particles. The last thing we need to talk about in this note section is the penetrating effects of these radioactive particles in terms of how much these particles can penetrate and to what degree they can cause some problems. Alpha particles can't penetrate a few sheets of paper or the outer skin cells. Enough exposure to our alpha particles can actually cause severe burns. So alpha particles can't penetrate our skin at all, but if we're exposed to enough of them for a long enough period of time, they can definitely cause some problems with severe burns. For beta particles, these can penetrate more than alpha particles, and these can be stopped with a sheet of aluminum or plastic. And lastly, the gamma rays and X-rays, these can penetrate more, but can be stopped by a thick lead shield. That's why if you've ever gone to get an X-ray, they put a lead apron over you, and that's to stop the X-rays from being penetrated to that certain area of the body, and it allows some form of protection. Both gamma rays and X-rays are very dangerous to living organisms, and that's why if you are a doctor or nurse dealing with X-rays on a regular basis, or even pilots of commercial airliners, they have to take into effect how much radiation they receive because it can cause serious health effects. In terms of looking at this on a diagram, you can see that the alpha particles are stopped by our skin cells, our outermost skin cells, where beta particles can penetrate through our skin, and those can be stopped with a piece of aluminum. And then our gamma rays and X-rays, of course, can penetrate all of the above and can be stopped with a sheet of lead. And then we're just simply not going to talk about the neutrons. We'll save that for when you get to a chemistry course. But you do need to know the penetrating effects of what can stop each sort of particle based on this diagram. That's going to do it for this note section on our introduction to radioactivity, where we talked about the people involved with discovering radiation. We talked about the different types of particles as well and their penetrating power. If you have any questions throughout anything in this note section, make sure you get those questions asked so that way we can clarify any points of confusion for you.